I'd like to talk about the acidity of aromatic hydrocarbons and the acidity of phenols and benzoic acids. If you'll remember back when we were talking about aromaticity, we discussed the relative acidity of these two compounds, cyclopentadiene and cyclopentane. And what we said was that cyclopentadiene was a lot more acidic than cyclopentane because the anion it produced was a lot more stable than this one. The reason this anion is more stable than this anion is because it's aromatic. This anion is not aromatic. In fact, the stability difference in these anions is so great that it causes a huge acidity difference in the original compounds. In fact, we can say this compound is 10 to the power of 40 times more acidic than this one. I get that by doing 50 minus 10, and because it's a log, it's 10 to the power of. So it's 10 to the power of 40 times more acidic than this one. Now, the other thing we know is that the more stable the anion is, the more acidic the original compound is. And since this anion is a whole lot more stable than this anion, this compound is a whole lot more acidic than this compound is. This time to the tune of 10 to the 40. If we take a look at phenol, this is phenol here, it's got the benzene ring with the OH on it, and we compare its acidity to cyclohexanol. We see that cyclohexanol has a pK of 14 and that phenol has a pK of 10. So we see that phenol is about 10 to the 4 times more acidic than cyclohexanol is. Now the reason for this is because we can look at the anions and we can see this anion is capable of a lot of resonance. There's an aromatic ring here, so the negative charge can be here, it can be here, it can be here, and it can be on the O. Whereas with the cyclohexanol, we notice that the O negative can only ever be in this position here. The negative charge can only be on the oxygen. Let me go back and show you this on the PowerPoint. You can see that this is phenol. The negative charge can flit to here, can flit to here, can flit to here, or it can be on the O negative. If the negative charge can move around, that means it's going to be more stable. If the anion is more stable, that means the compound is going to be more acidic. And what I want you to remember is the lower the pKa, the stronger the acid. Alright, so let's go back to the PowerPoint. Sulfonic acids have a similar structure to sulfuric acids and are thus highly acidic. So this is sulfuric acid here. It has a very low pKa. In fact, it's negative. That's because it's a very strong acid. Now, the reason it's a strong acid is because if you take that H off, you'll be left with a negative charge, and that negative charge can then resonate with both of these double bonded oxygens. That's what makes sulfuric acid such a strong acid. Compounds like this, sulfonic acids, tend to have a similarly high acidity as well. We can also look at benzoic acids, and benzoic acids are a little bit more acidic than compounds that are not aromatic, or similar compounds but are not aromatic. If we take a look at this compound here, if it doesn't have the aromatic ring, we see it has a pKa of 4.73. This one, benzoic acid, which has the aromatic ring, has a slightly lower pKa, 4.23. So this one is slightly more acidic than this one. And the reason for that is because the anion we get from benzoic acid is just a tad bit more stable than the anion we get from this compound, and that's just due to the presence of the aromatic ring. The other thing that we can look at is we can now compare the placement of different groups on the aromatic ring and analyze the effect that has on the stability of the anions that we get formed and therefore the acidity of the compounds from which they came. Alright, so I've taken this and I've now drawn their anions over here. Alright, so here we have benzoic acid. This is garden variety benzoic acid with nothing attached to the ring. You can see that the pKa of benzoic acid is about 4.23. Now what I've done is I've thrown a nitro group onto the ring. Now what we know about nitro groups is that they are deactivating, and being deactivating, what they will do is they will suck electron density out of the ring. And if they do that, then they can stabilize any negative charge we get up here. So pulling electrons out of the ring makes the ring more positive, which stabilizes this negative charge better. Now since this anion now is more stable than the anion we've got down here, we see that we get an increased increased acidity, which is a lower pKa value. So we've got 3.49 versus 4.23, indicating that this is a stronger acid than this one is. Now again, the reason for that, this anion is more stable than this anion due to the electron pulling effect of the deactivating group. Now if we put an activating group on the ring, you can see that the opposite thing occurs. Now activating rings will add electron density to the ring, making the ring more negative. Now since this ring is more negative now, it's going to be destabilized relative to this one. Now since this anion is less stable than this anion, and this acid is less acidic than this acid, so we see we've got a higher pKa value here, and that's due to the fact that we've got an electron donating group, and that's going to be pushing electrons into the ring and destabilizing this anion. Remember, the more stable the anion, the more acidic the compound is going to be. We notice a similar effect with phenols. Now phenols are not quite as acidic as carboxylic acids, but we see the same effect is occurring here. You'll notice that the nitro group will stabilize the O negative by pulling electrons out of the ring, whereas the OMe group will destabilize the anion by pushing electrons into the aromatic ring. And you can see the effect that that has on the pKa's. This one has a pK of 7.15 compared to the 10.00 for the unsubstituted phenol. Then when we throw the OMe group on, you can see that that lowers the lowers the acidity by raising the pKa and producing a less acidic compound.